Hi everyone, welcome to
amazing channel of Brilliant Katha.
When you're rubbing one body with another body, electrons are transferred from one object to another object. So this type of electricity is been given a name.
halogen connected carbon sp3, then it's connected to benzene. See all of you, halogen connected. What is this carbon hybridization? Full single bond sp3, see then a benzene ring.
Denominator poles shouldn't be included in the denominator poles. That means the denominator, these -1 and -5 should never be included in the solution.
Homocircle caudal fin. It's giving two equal lobes. But in case of cartilage fishes, look at here, one big lobe is there, one small lobe is there. You cannot cut into two equal half this fin.
Very good evening everyone, and welcome to another live session of discussion, MCQ discussion. Today we discuss modern physics, like dual nature of matter and radiation, atoms and nuclei, 3 chapters together. So for the next 1 hour, be with me. Leave your answers in the comment during discussions. Okay, so let's go on to the discussion, straight to the concepts. First, a few questions will be from dual nature of matter and radiation, the first chapter. And when we go through the chapter wise weightage, we know dual nature of matter and radiation is one single unit, whereas atoms and nuclei together is another unit. And we expect more questions from dual nature, this chapter, the first chapter, than the number of questions together from atoms and nuclei. And when you go through the past papers, you can see more number of questions are coming from dual nature comparing to atoms and nuclei together. So we will have more questions from dual nature in our discussion also, followed by atoms and then nuclei. That is what we planned in today's discussion. Okay, and when you go through the concepts of dual nature, see the major concept that we have to go for is photoelectric effect. This is the key concept of the chapter, right? More than 90% of the concepts are related to this particular phenomenon, and that is the basic phenomenon. That the basic thing is electronic emission. A special type of electronic emission is called photoelectric emission, right? And in photoelectric effect, we discussed a lot of things, and a complete like a comprehensive study of that particular topic will help you to solve most of the questions we get from this particular chapter. Okay, and more both conceptually and numerically, both questions. When you go through the past papers, you can see we get conceptual questions and numericals, right, from photoelectric effect repeatedly. Okay, and the other one is de Broglie hypothesis. The second important equation is de Broglie hypothesis. Only 2 important concepts in this chapter, and we have, like a more detailed study of photoelectric effect. As I told you, we know how effect of intensity of radiation, intensity of radiation, how it affects photoelectric emission, and potential difference, applied potential, how it affects photoelectric emission, and frequency of incident radiation, how it affects photoelectric emission. So that experimental study of photoelectric emission that revealed a lot of concepts, like we got a complete clear picture of that photoelectric emission from the experimental study part. So that concept should be perfectly fine if you want to solve questions from like photoelectric effect. See, not only conceptual questions, even if you want to touch the numerical questions, you should have a proper understanding of what is photoelectric effect, and I hope you remember the equations. Okay, so we know effect of intensity, we know photoelectric current or number of photons emitted per second from a photosensitive material is directly proportional to the intensity, but it is independent of frequency, right? Yes. And effect of frequency, which quantity is affected by the frequency? Yes, the frequency is, frequency of incident radiation decides the kinetic energy of the emitter electrons. Yes, yeah, yes. Hi Shilpa. Yes, we have some friends joined in the group, like in the chat. Yeah, keep sending messages, keep responding to the questions. Okay, fine, thank you. And here, frequency, as I told you, frequency like directly affects the kinetic energy of the emitter electrons, photoelectrons, and we know. So these experimental study, as I told you, we have very will help you to solve most of the questions. And from that part, we have Einstein's photoelectric equation. Kinetic energy is going to be h nu minus work function. We know where nu is the frequency of the incident radiation, h is the Planck's constant, w naught is the work function of that particular photosensitive material, ke is the kinetic energy of emitted radiation, emitted electron. Yes, and this can be hc by lambda minus w naught also, where nu is equal to c by lambda. These equation, most of the cases we use this equation to solve, like to find out kinetic energy or to find out work function. See, this equation is one of the equation we repeatedly use in our numerical question, right? And if you come to the de Broglie hypothesis, the last part of the chapter, from that we have expression for de Broglie wavelength, lambda is equal to h by p, right, where h is the Planck's constant once again, p is the momentum, linear momentum, right? And this equation has some alternate forms. P can be replaced by kinetic energy. Momentum and kinetic energy are related, like lambda is equal to h by root of me, and kinetic energy of any charged particle can be root of 2m into qv, where v is the accelerating potential. We know these many equations only we have from the chapter, and that help us to solve almost all the questions, right? And we had some graphical representation of these effects, how intensity affects the photoelectric emission, what is the effect of frequency, how applied potential affects, these kind of relations we represented in graph, and we have some sample questions. We will go through them. Okay, yes, let's start with question number 1. Right, the first question is about a light of frequency nu. Okay, it is a frequency nu. Yes, is incident on a metal surface whose work function is w naught. We know w naught, usually we use that term to represent work function. The kinetic energy of emitted electron is k. K is the kinetic energy, right? Then the frequency, if the frequency of the incident light is doubled, then the kinetic energy of emitted electrons will be. See, what we are trying to find? Kinetic energy of photoelectron after doubling the frequency of incident radiation. See, initially it is given that initially the frequency was nu, right? Incident frequency was nu. At that time, we got kinetic energy of emitted electron as k. As I told you just before, kinetic energy equation Ke is equal to h nu minus work function. That is the equation, right? Yes. So this is the basic equation we have to use. Question says when frequency was nu, kinetic energy Ke is just k, right? As per the question, it is just k, right? So we can say k is equal to h nu minus work function. Equation number 1. Okay, fine. So far so good. What happens next? Next, we double the frequency. As per the question, the kinetic energy of emitted electron is k. Then what happens later? Frequency of incident light is doubled. So this nu we have to change into 2 times nu. If so, what will be the new kinetic energy is the question. So let me take that kinetic energy as k dash. Okay, the new kinetic energy after doubling the frequency. So it is going to be h into 2 nu minus work function. So we can say this is just 2h nu minus work function. This is k dash. Okay, but look at the options given. Options are just comparing this k and the new kinetic energy with the old kinetic energy. It is less than k or more than k, between k and 2k, or more than 2k. See, that's the options given. So we are trying to relate them now. Okay, so this is our second equation. What happens if I subtract equation number 1 from 2? 2 minus 1. LHS is going to be k dash minus k, right? K dash minus k equals to 2h nu minus h nu. 2h nu minus h nu is going to be just h nu. correct, h nu. And what happened to work function part? Minus work function, minus of minus work function becomes cancelled. So this is it. K dash is equal to, what is K dash? K plus h nu. So one hint we got here, K dash is going to be more than K, right? More than K, right? But we are still not sure about this h nu. How much this h nu will be? See, what is that h nu from the equation number 1? From equation number 1, what is h nu? H nu is going to be K plus, right? I say h nu is equal to K plus work function, correct? K plus work function. Look at the first equation. First equation says K is equal to h nu minus w naught. Yes. So what is h nu from that? K plus w naught. If you substitute that h nu in the equation, we get K dash is equal to, what is K dash? Already we have a K on the RHS. K plus, instead of h nu, I should substitute K plus work function, right? K plus work function. So what is altogether on the RHS? 2K plus work function. That is, the new kinetic energy is equal to 2 times the kinetic energy plus something. What is that something? Work function actually, right? Yes. So this is how we can relate initial and final kinetic energies. So what is your option? K dash is going to be 2K times W naught. So we can say your new kinetic energy is more than 2K, right? Option B, more than 2K. Yes. Yeah. So more than 2K means 2K plus W naught. So we get 2K plus something. So it is going to be more than 2K. That is your correct answer, option B. Right. So we just consider 2 different cases. In the first case, frequency was just nu, and second case, frequency of incident radiation is doubled. Right. So what do we expect actually? It may be 2 times the kinetic energy, right? Yes, but it is not 2 times the kinetic energy. It is more than 2 times the kinetic energy, because what is the reason? Because we doubled only this frequency. Work function is still the same only, right? Work function is constant for a given photosensitive material. Yes. So we found the final answer as option B. I hope it is clear. Yes. Okay. Right. So let us move on. Question number 2, the next question. If photons of frequency nu, yes, this is also nu, okay, photon of frequency nu are incident on the surface of metal A and B of threshold frequencies nu by 2 and nu by 3 respectively. The ratio of maximum kinetic energy of electrons emitted from metals A and B is. So we have to find out what is the maximum kinetic energy of emitted electrons in 2 different cases. I mean 2 different materials A and B. Both of them have the same incident frequency, right? I am going to use same incident frequency, same radiation to irradiate both A and B, surface of A and B. What will be the ratio of maximum kinetic energies? Still, we have to use the same equation, right? Kinetic energy equation, Einstein's photoelectric equation. Kinetic energy of emitted electrons, maximum kinetic energy of emitted electrons is equal to h nu minus work function, right? H nu minus work function. And here you are not given the work function, instead you are given the threshold frequencies, and we know how to calculate threshold frequency. Threshold frequency of any work function of any photosensitive material is going to be h into threshold frequency, h into nu naught. Correct? H nu naught. That is the work function. That is how we calculate. So we can say kinetic energy is equal to h nu minus h into threshold frequency nu naught. Done. So now what we have to do? H, the incident frequency is same for both the cases, only threshold frequency is different. We will form 2 equations and we solve them, right? Yes. So for the first case, in the first case, what is the threshold frequency given? Nu by 2 for A, right? So we can say kinetic energy of A is going to be equal to h nu minus h into what is the threshold frequency of A is nu by 2, correct? Nu by 2. So if you simplify this, we get h nu by 2, right? H nu by 2 on the RHS. Kinetic energy of A is h nu by 2. If you do the same thing for the second one, kinetic energy of B, the second material, kinetic energy of B is going to be h nu, same incident frequency, but threshold frequency is different this time, nu by 3. So h nu by 3 correct? So 3h nu minus h nu, we get 2h nu divided by 3. This is kinetic energy of B, equation number 2. Okay, so now you are asked to find what is the ratio of kinetic energy of A and B, and that is now easy. We can just take the ratio of equations 1 and 2, correct? Yes, so we will go for equation number 1 by equation number 2. So kinetic energy of A divided by kinetic energy of B is equal to, see, h nu divided by 2, h nu divided by 2, the whole divided by 2h nu, 2h nu divided by 3, correct? We can cancel that h nu from either side, right? And there will be 3 by 4. This is going to be just 3 by 4. So if you have an option 3:4, that is your correct answer, and that is option B, right? Option B. Yes. So as I told you, most of the numerical questions we get from photoelectric effect is based on kinetic energy equation, okay? Einstein's kinetic energy equation, and we can just simplify we can solve it very easily using that equation, if you remember that equation correctly. Yes, moving on to the next one. Next one is a graph question. Yes, Smriti. Yes, I saw your answer. Keep going. Right. Variation of photoelectric current with collector plate potential for different intensities I1 and I2. Okay, so you are given two different intensities I1 and I2. And frequency is fixed. Frequency is fixed. We consider potential applied photoelectric current and collector potential graph. I hope you remember the graph. So you can see in the options you are given almost all the graphs in the same way. We know when you take photoelectric current along y-axis and accelerating potential along x-axis, retarding potential along y-axis, we know the current, even at zero applied potential, what happens? Even at zero applied potential, there is a non-zero current. Some of the electron has enough kinetic energy to move by themselves from photosensitive material to the metal electrode, so that they constitute a photoelectric current even at zero applied potential. See, when you increase accelerating potential, current increases from that value and it becomes saturated. We know, right? Current becomes saturated. Whereas when you flip the cell, when you reverse the potential, it is called the retarding potential. That potential will pull those electrons back without letting them go to the other side, and so it reduces the current. Finally it becomes zero. This was called the stopping potential, at which we didn't expect any current in the circuit, right? Current reduces to zero. This is the shape of the graph. Yes, this is the shape of the graph, current versus potential graph, and you're given in all the options except in the option A, they are given almost in the same shapes, and definitely option A is not our answer, of course. That is not the matching shape. And look at the other graphs. One way or other they are somewhat similar, right? Yes. So now look at the question. We are going to fix the frequency. If the frequency is fixed, what hint is there in that particular term? Like what can you understand from this? Fixed frequency means frequency of incident radiation is a constant. We know whenever frequency is a constant, stopping potential will not be affected, because stopping potential is proportional to the kinetic energy of photoelectrons, right? Yes, if you want to change the kinetic energy, you have to change the frequency of incident radiation. Here frequency is fixed, so there will not be a change in stopping potential. Yes, so B is also not an option because we have two different stopping potentials given in the option. Done. So then either C or D. See, the only difference between C and D is I1 and I2 are just interchanged. So the lower graph is given for I1 intensity, upper graph, the greater current is given for like I2 intensity in option C, and in option D it is given the other way around. So how will you understand which one is the correct option? We know photoelectric current is directly proportional to the intensity, as I just reminded you. Yes, they are. Yeah, yes, many of you already identified the answer. So now intensity photoelectric current is directly proportional to the intensity, so more current should be marked for greater intensity. Question says I1 is greater than I2, so more current should be allotted for I1, and option D is the correct answer. Yes, Option D is the correct answer, and we ruled out all the wrong answers. See, it's not about solving this particular question. We are trying to understand the concept also behind it, right? Yes, keep going. Now, moving on to the next. Another graph question. See, again, it is a photo current and collector plate potential, and it is a simpler question comparing to the previous one. For the graph shown, F denotes the frequency of incident light. F stands for the frequency. Yes. So then, what is the correct order of those frequencies? In the options you are given, FA greater than FB greater than FC, that kind of comparison relation is given. So you have to identify the exact relation between the frequencies from the graph. Okay, right. And just now I told you, whenever we change the frequency, what will be affected? Stopping potential is affected, and you are given 3 different stopping potentials in the graph, right? For A, stopping potential of A is the most. Correct? In the graph, stopping potential of A is the most. We know stopping potential EV0 is equal to kinetic energy, right? Kinetic energy, and that kinetic energy we know is proportional to frequency of incident radiation, right? This is how are they related. Stopping potential EV0 is equal to kinetic energy, or we can say V0 is proportional to kinetic energy. That is proportional to frequency of radiation. So greater the stopping potential, greater the frequency of radiation. Yes. So now you can easily identify greatest is for A. So this is frequency of A, and this is frequency of B, frequency of C. Their values are like, you know, in the order. A is the most, then C is the least. So we can say FA greater than, FB greater than, FC, and A is the correct matching option. Greater the frequency, greater the stopping potential, because greater the kinetic energy will be, right? Yes, kinetic energy and stopping potential are directly proportional. Yes. So graph questions, be very careful, because they look very similar when you go through, when you just look at the graph and read the question properly. Try to understand what are the quantities taken along x and y axis. So, right, the same graph may give you some different information if you change, you know, these quantities, x and y axis. Yes. Right. Moving on to the next. Photons of energy 3.2 electron volt are incident on a photo sensitive surface. If the stopping potential of the emitted electron is 1.5 volt, stopping potential is given. Stopping potential is 1.5 volt. I want to tell you something important here before going to the solution, and let us complete the question. The work function of the surface is, you are asked to find what is the work function of the surface. Right. Work function, if you want to calculate, by giving what? Energy, incident energy. Incident energy is already given. Stopping potential is given. Yes, stopping potential is given. And you are asked to find what is the work function. So how can we relate them? Again, Einstein's photoelectric equation help us to solve this question. Look at this. Here stopping potential is given. You may know this, and you have to remember this, you know, that will make this solution very easy. Whenever stopping potential is given, if stopping potential V0 is given as 1.5 volt, that means that particular electron has a kinetic energy just 1.5 electron volt. If stopping potential is 1.5 volt, what is the kinetic energy of that particular electron? 1.5 electron volt. Yes. If kinetic energy is given as 2 electron volt, for example, what will be its stopping potential? It will be just 2 volt. Okay, so from stopping potential value, we can easily infer what is the maximum kinetic energy of that particular emitted electrons. See, emitted electrons has a potential energy 1.5 electron volt. That is not given in the question. In the question, they are given already, only what? The stopping potential is 1.5. If stopping potential is 1.5 into E, right? You know, EV will be what? Its kinetic energy. 1.5 volt, 1.5 EV is the kinetic energy. So now it is easy. Kinetic energy is given, right? Kinetic energy of photoelectrons is given. Incident energy H nu is also given. that is 3.2 electron volt. Yes, both are in electron volt also, nothing to worry about. Now what is the quantity to be calculated? Work function. Now it is a direct substitution and simplification, just complete it. We know kinetic energy is equal to h nu minus work function, so we have to find out the work function, which is incident energy minus kinetic energy. Incident energy are given in the question, which is 3.2 electron volt. Yes, minus what is kinetic energy? We found out from the stopping potential, which is 1.5, right? 1.5 electron volt, right? So then that will be 1.7 electron volt, which is given as option B. See, so only one simple concept made that question very easy. If you know how kinetic energy can be understood from the stopping potential value, that question is already solved, right? Then just substitution and simplification is remaining, right? So that is about Einstein's photoelectric equation. Yes, Hridya. Okay, Diya, yeah, correct only. Come on. So then moving on to the next question. Photoelectric surface. A photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and lambda by 2. Two different wavelengths, okay, lambda and lambda by 2. If the maximum kinetic energy of the emitted photoelectrons in the second case is 3 times than in the first case, the work function of the surface, work function of that particular photosensitive material is to be calculated. Your given Planck's constant is h and c is the speed of light. Both of them is very familiar to us, right? And thanks for the information in the question. Anyway, see, these options are, there is no numerical values, just some combination of h, c and lambda. Okay, so instead of frequencies of incident radiation, so far in almost all the questions they were given like frequency of incident radiation, but this case they have given what? Wavelength, right? So be very careful. When we come to the wavelength part, we know kinetic energy K, let me take it as K, kinetic energy of emitted electron is equal to what? It is h nu minus work function. That is the equation, but not frequency this time, it is wavelength. So what can we do? We can just change this h into c by lambda, right? That's it. It's c by lambda, right? So that, in the first case the wavelength was lambda only, so that is k, only k, kinetic energy. In the second case, the same photosensitive material is irradiated with another frequency, I mean another radiation of wavelength lambda by 2. What will be its kinetic energy? Some k dash, some other kinetic energy. h c by lambda by 2 is minus work function. Work function will not be changed because in both the cases we use the same photosensitive material. So work function W naught, here also work function W naught, but we use two different incident radiations. One has wavelength lambda, second one has wavelength lambda by 2. One more information is given in the question. How are these kinetic energies related? Look at that. Initial kinetic energy. See, kinetic energy emitted photoelectrons in the second case is 3 times than in the first case. So in the second case it is 3 times than in the first case. So k dash we can write as 3 times k, right? 3 times k. K dash is going to be 3 times k, right? So we can say 3k is equal to 2 hc by lambda minus work function, right? So we got two equations, like this is the first equation and this is the second equation, right? Now we have to find out omega, I mean W naught from this particular like two cases, like we have kinetic energy initial, kinetic energy final, and we have to find out what is the work function from these two equations. So what can we do? So we can just go for ratio of these equations. If we add them up, we get 3k plus k is equal to 2 hc by lambda plus hc by lambda minus 2 work function. So we get 3 hc by lambda minus 2 work function is 3 times k. right? Okay, so then what can we do? How will you find out HC by, we have to find out work function only from this. So we write 3k is going to be 2hc by lambda minus work function is equal to 3hc by lambda minus 2 work function. So if you take this into the other side and the we get minus work function is equal to minus hc by lambda, right? Yes, so we just substituted the value of 3k here, that's it, and when we cancel those minus signs we get work function finally w naught is equal to hc by lambda, right? See, we just solved these two equations in different ways. You can solve those equations. I just added them up, and I equated 3k value, I substituted and simplified. Work function is obtained as hc by lambda, which is option B, right? hc by lambda. Okay, so the point you have to remember here, when you change frequency into wavelength, your h nu term should be converted to hc by lambda. Yes. Yeah, exactly. Yes, flip-flop. Right, Sanjay. HC by 200. Yes, exactly. So many of you already answered the questions. Yes, keep going and keep posting the answers. Okay, right. So let us move on to the next question. Yes. Now the next one, in a photo emission, frequency of incident radiation falling over a surface above the threshold frequency. Okay, but intensity is very low. Yeah, look at the situation. We have an incident radiation. That incident radiation has a frequency which is more than threshold frequency. Okay, that is okay, fine. But what is the like concern here about the intensity? Intensity is very low. Right, then you are asked to select what happens next, like from the options, from the 4 options, what can be the correct matching answer for this particular situation. Yeah, can you please identify what is the correct answer from this? See, the options are time required will be large, right? That means to emit electrons from the metal surface, the electron will take some more time because intensity is very low. That is what they say, right? Second option, time required will be small than the normal case. It will take smaller time to emit out of the metal surface. Okay. Third option is process is instantaneous whether intensity is high or low. That is option C. That means in that case whether intensity is high or low, it doesn't matter. That is what option C says. And finally, the fourth option, photoelectric emission does not occur. So what do you go for? Yes, Yuvraj. Diya. Tanvi. Yes. Hi Tanvi. Hridya. Yes, Smriti, that is a perfect option. Yes, most of you are almost like, given me the correct answer only. It's option C, because we know as the part of law of photoelectric emission is an instantaneous process, right? There is no time lag. Even if you don't know what happens in this particular situation, you may be able to solve this question by looking into the third particular option only, right? Because that says it is instantaneous, and we know photoelectric emission is instantaneous process, and you cannot like go wrong for this question, because only this particular term itself help you to find out the exact matching option from the given 4. Yes, and see, actually what happens here, intensity is low. Does that matter? No, exactly. See, incident wave or incident frequency, if incident frequency is more than threshold frequency, according to the concept, the electron should be emitted, right? Electron should be emitted if there is a radiation incident on it. Yes. Whether intensity is less or high, it doesn't matter. But what will be the difference if intensity is high? More electrons will be emitted. Yes. Yeah, more electrons will be emitted. Good. Right? But for low intensity also electronic emission possible, right? But number of electrons emitted will be less. So remember, photoelectric emission is instantaneous. That particular term itself helped us. Okay, anyway, fine. So that is answer for this question. Option C is the correct answer, right? Okay, right. So next one. They're talking about a graph is plotted between the stopping potential on y-axis and the frequency of incident radiation on x-axis. For a metal, the product of the slope of the straight line obtained and the magnitude of the charge we are going to multiply two quantities. Which are they? One, slope of the straight line graph. Yes. When we plot a graph, they say we get a straight line. Its slope is multiplied with what? Charge of an electron. Slope into charge. You must have identified the answer by the time, because we discussed that graph in detail. Like, you know, we have similar graphs, like two similar graphs. Slope are different if you change the quantities along x and y axis. Yeah, I'm talking about kinetic energy versus frequency graph and stopping potential versus frequency graph. Here it is stopping potential versus frequency graph. That is what they talk about. How will you draw stopping potential versus frequency graph? Stopping potential is taken along y-axis V0, right? And frequency is taken along x-axis. See, nu is the frequency taken along x-axis. So what is the shape of the graph? We know stopping potential is directly proportional to the frequency of incident radiation, right? Yes, because kinetic energy, stopping potential is proportional to kinetic energy. Kinetic energy is proportional to frequency. That is how we related them, you know. That's how we remember. So when you change frequency, stopping potential will be changed. Directly proportional, the graph should be a straight line. But you can't start the graph from the origin. Why? What was the problem? Like, why can't we start the graph from the origin? Tell me. From where should I start the graph then? See, I cannot start from zero frequency. Why? Because for photoelectric emission to happen, there is a condition: incident radiation should have a minimum frequency below which no photoelectric emission is possible, right? Yes, so that is called threshold frequency, and we have a straight line passing through that point. This is the graph they are talking about. Yes, and what was the wave? I mean, that what was this quantity at the point here? That is threshold frequency, nu naught, right? Threshold frequency. Yes. What is slope of this graph? Slope of this graph, the quantity we are looking for is slope of the graph into charge of electron. So now you can just have to find out what is slope of this graph. Just multiply that with charge of electron. One of the matching option will be obtained, right? Yes, Sanjay. Yes, Hridya. Yes, exactly. Threshold frequency. That was a point from where should I start the graph, right? Exactly. See, now this equation, we know Einstein's photoelectric equation, kinetic energy is equal to h nu minus work function. We know kinetic energy can be represented as EV naught, which is h nu minus work function, correct? Yes. So V naught is equal to, if you want to take V naught alone on LHS, E is taken to the other side, h by E into frequency minus W naught divided by E, right? I have taken that E to the RHS, that's it. Okay, and this is in the format Y is equal to mx plus C, right? Mx plus C. See, along y-axis, what we have taken? Along y-axis, we have taken stopping potential, V naught. Yes. Along x-axis, what do we have taken? Frequency. Yes, frequency. Then what is this quantity stands for? H by E. That is the slope of the graph, right? Yes, H by E is the slope of the graph. So slope of the graph is H by E. We have to multiply that slope with charge of electron. One more E into E. See, E gets cancelled and we get Planck's constant is revealed. Yes, so this is the answer. E gets cancelled. So remembering the slope of stopping potential versus frequency graph will help you to save your time, right? We know V naught versus frequency graph, slope is h by E. That is how we learned it, we remembered. Yes, and if I change this V naught into kinetic energy, graph looks exactly the same way, similar, like exactly the same shape, but the slope value will be different. Do you remember what is the slope of the graph if I change stopping potential into kinetic energy? Anybody? Yes, Sanjay. Yeah, we already identified the answer for the question. See, if I change this V naught into kinetic energy, what will be the new slope? Yes, so kinetic energy, stopping potential is replaced by kinetic energy, then the slope will be exactly obtained from this equation. Kinetic energy is equal to h nu minus work function. Yes, it is h only. I started getting answers. It is Planck's constant. Yes, h is the Planck's constant. That will be the slope. So that is what I told you before. When we get graph questions, go through that question clearly, like go observe the graph and make sure what are the quantities taken along x and y axis. If I change the quantities along x and y axis, you will get different outputs, like different slopes and y-intercepts also. So for this question, Planck's constant is the answer, right? Okay, fine. Let us move on to the next. De Broglie wavelength. Okay, so I am coming to last part of the photoelectric emission, like that particular chapter. De Broglie wavelength equations I already mentioned before, right in the beginning. Here they say de Broglie wavelength of a particle of kinetic energy k is lambda. Yes. So for de Broglie wavelength questions, the equation that you are going to select is very important. We have lambda is equal to h by p. Lambda is equal to h by root of 2me, right? And lambda is equal to h by root of 2m into qv. The only difference is like P is replaced by kinetic energy. Momentum and kinetic energy are related like this. Inside that root of term, there is a kinetic energy. Kinetic energy is replaced by QV. We know these equations. And in the given equation, in the given question, you are given kinetic energy is what? Kinetic energy was K. For that particular particle, what is the wavelength? De Broglie wavelength? Lambda. So they are talking about kinetic energy, so I have to opt the second equation, right? Yes. So wavelength of, what will be the wavelength of the particle if kinetic energy is K by 9? Only kinetic energy is going to be affected. If I take that equation, lambda is equal to h by root of 2m into E. See, in these two cases, only what is changed? Kinetic energy is affected, right? So we can say here h is a constant, 2 is a constant, same particle, so its mass remains the same. Lambda is inversely proportional to root of E. Correct? So what will be lambda dash inversely proportional to? The new kinetic energy E dash. Right? So we can take the ratio. What will be lambda by lambda dash? Lambda by lambda dash is going to be root of E dash by E. Correct? Root of E dash by E. What is the new kinetic energy? E dash is going to be E by 9. So I can say, see, E dash is going to be K by 9. And what was the initial kinetic energy? It is just K. So K gets cancelled. Root of 1 by 9 is going to be what? 1 by 3. Lambda by lambda dash is 1 by 3. So what is lambda 3? Lambda dash. Lambda dash is going to be 3 lambda, right? 3 lambda. So 3 lambda is one of our options, option C. So only one thing you have to be careful, which equation we have to select to solve the question. That is the turning point of the solution. Select the correct equation by looking into the question and solve it. Okay, fine. Next question, again de Broglie wavelength. Electrons used in an electron microscope are accelerated by a voltage of 25 kilovolt. Accelerating potential is given, right? Accelerating potential 25 kilovolt. Yes, if the voltage is increased to 100 kilovolt, then de Broglie wavelength associated with the electron would. What happens when we change the that particular accelerating potential? So here in this case we have to go for the third equation, lambda is equal to h by root of 2mqv. How do you know we have to select this equation? Because the question is talking about accelerating potential. Yes, so we keep it is electron in both the cases, mass remains the same, charge remains the same, h is a constant, 2 is a numerical constant, lambda is proportional to 1 by root of v. And lambda dash, the new lambda, will be proportional to 1 by root of new potential. If you take the ratio exactly like in the same way like in the previous question, we can say lambda by lambda dash is equal to root of v dash by v. V dash by v. So look at this ratio. Initially it was what? 5 times, right? 25. So 25. And v dash is the new accelerating potential, which is 100. So I can take this as 100 divided by 25. See, we get 4, root of 4 is going to be 2. So what is the new lambda? Lambda dash is going to be lambda by 2. Correct? Lambda dash is going to be lambda by 2. So what happened to the wavelength? It decreases by 2 times, right? So that is the correct option, option A. Got it? So this is how we do like de Broglie wavelength questions. I hope that's the last question from de Broglie wavelength. Yes. And Yes, one more question we have, so we'll just quickly go for that too. Proton and an alpha particle are accelerated through the same potential difference. Ratio of de Broglie wavelength lambda p to lambda alpha. See, proton and alpha particle, proton and alpha particle. So when we go to the equation, accelerated through the same potential difference, so we have to use the same equation which we have used in the previous question. Lambda p is directly proportional to, or it is equal to h by 2 mq into v, right? H by root of 2 mq into v. So here h is a constant, 2 is numerical constant. We know mass of proton and alpha are not the same, so we cannot take that as constant. Q is also different. And what about v? V is same, like they are accelerating through the same potential difference. We can say lambda of p is directly proportional to, or lambda of that particular particle is proportional to 1 by root of charge into mass. So we can say lambda of proton is proportional to 1 by root of mass of proton, charge of proton. What about lambda of alpha? Proportional to 1 by root of mass of alpha, charge of alpha. So if you take lambda p to lambda alpha, ratio lambda p by lambda alpha, see, they are the other way around, ratio will be the other way around, m alpha q alpha divided by m p q p, right, square root of. Yes, now let us substitute. What is mass of alpha particle? 4 atomic mass unit, right? 4 particles, 2 protons and 2 neutrons. We remember this, yes. And 4 atomic mass unit is the mass. And what is the charge of alpha particle? 2e, right? Divided by mass of proton is just u and e. Got it? Exactly. Square root is there, yes, definitely. And we can say what is lambda p by lambda alpha ratio. What is it? So you can cancel u and e. We get root of 8 by 1. So your option D is the correct answer. Okay. So this is how we do questions from de Broglie wavelength. So we have to consider the exact equation by reading the question, identify the correct equation we have to use. Okay, fine. Now, we don't have much time, so we'll try to do as many questions from atoms and nuclei. So we know from atoms part, atom models we discussed, started with the atom models. We know J.J. Thomson's atom model. We started the discussion of the chapter atoms in the backdrop of that particular concept, right? Yes, J.J. Thomson plum pudding model, yes. And alpha particle scattering experiment was the first topic we explained, and there we need 2 concepts. One is distance of closest approach, right? Closest approach, just remember what is it, and like impact parameter. These are the 2 quantities. Impact parameter, that are the 2 quantities we mentioned in the alpha particle scattering experiment, using which Rutherford explained that particular phenomenon, right? Then Rutherford atom model, its drawback. But we focused more on Bohr atom model. The whole chapter was a detailed study of Bohr atom model. We knew how to find out radius, okay? Radius was proportional to n square. Energy of nth energy level was found to be proportional to minus 13.6 by n square, right? Electron volt. So these kind of equations we derived from Bohr atom model. And remember the 3 postulates of Bohr atom model and its mathematical form. If you learn that properly, you can like solve almost all the questions coming from that particular part, right? Then the spectral lines, hydrogen spectrum, the 5 spectral series, its like wavelength, maximum wavelength, minimum wavelength, maximum frequency, minimum frequency, that kind of calculations. We have some examples. Okay, so we'll try to do some questions from that part also. And in nucleus, let me just go through that also. In nucleus, the profile of the nucleus, we made the profile of the nucleus right in the beginning. Profile in the sense how big it is, what is mass of the nucleus, like what is its density, these 3 quantities, like, and exactly we get 2 equations there. Those equations you have to remember, right? Radius of the nucleus is R0 a raised to 1 by 3, right? A is the mass number, and density is independent of mass number. That also we identified from that particular discussion, right? Then binding energy. This is the next particular topic we get numerical questions from, okay? Binding energy calculation. Then nuclear force, we have a detailed discussion there, and we have one of the important graph which repeatedly comes for 3 marks, binding energy per nucleon curve, right? Last year also it was asked for 3 marks. Then nuclear fission and fusion, basics of just these 2 nuclear reactions also we have revised. So we have some examples from this also, altogether 4 or 5 questions. So let us move on to the first question from atoms. It is about impact parameter, right? Sorry if I am rushing through because we are running out of time. The impact parameter of an alpha particle, yes, impact parameter of an alpha particle approaching a target nucleus is maximum when scattering angle is. We know what is impact parameter. If you know impact parameter, then you can easily solve this question. Impact parameter is the perpendicular distance between two straight lines, we know, right? An alpha particle is passing. We are sending them to the gold foil. Remember the alpha particle scattering experiment. So we send alpha particle towards the gold foil, and this is the initial direction of alpha particle, and we have a straight line passing through the nucleus parallel to that line. Yes, then the perpendicular distance between the two straight line is called the impact parameter, we know. Question says impact parameter on alpha particle is maximum. Impact parameter is maximum means that particular alpha particle is going along a line which is far away from the nucleus, right? Far away from the nucleus. If so, what will be the scattering angle? Why do alpha particles scatter? Because of the repulsive force from the nucleus, right? Nucleus repel alpha particle, both of them have positive charge. So because of that repulsion, alpha particle deviates from its path. That is called scattering. So if alpha particle follow a line, a direction which is far away from the nucleus, will there be much deviation? Yes, right? Will there be any much deviation in that? No. So alpha particle go undeviated. Option A is the correct answer, right? If impact parameter is large, scattering is 0. Right? There is no scattering. Yes. If impact parameter is small, scattering is large. If impact parameter is 0, we know that particular alpha particle bounces back. That is how we learned it, right? Yes. So first question, option A is the correct answer. Just a conceptual one, nothing to calculate. Okay. Question number 2 from atoms. If radius of first Bohr orbit is r, then radius of the second Bohr orbit will be. See, when we get these kind of questions, that is very easy. It is simply we can solve because we know the relation r is directly proportional to n square. Whenever you read this question, this relation will come to your mind, right? And we will be so confident we know how to solve it. But one of the repeating mistakes that we commit is make sure what is the orbit given, whether it is second orbit or second excited orbit. Right? Because if it is second orbit, we know it is n is equal to 2. Second orbit means n is equal to 2. Second excited means second excited orbit is actually third orbit, n is equal to 3. So in a hurry, we don't identify properly like which is excited or the normal energy level they are talking about. So make sure, don't commit mistake. It's a very simple question. So because of this n value change, you may lose that mark, so be careful. Okay, so just remember this is not required for the solution of this question. Okay, don't be confused. Here it is just second orbit. Fine. So what is second orbit about? First radius is r1 is proportional to 1 square, which is given as r. So what about r2? R2 is proportional to what? It is actually R2 is equal to R0 into n square, right? So it is going to be 4R0. What is R0? R0 is the radius of the first orbit, right? That is R given in the question. So R2 is going to be 4 times R, which is option C. Correct? Yes. So be careful about that given energy level, whether it is like second orbit or second excited orbit. Okay. So we be careful. Now, next question. About energy of hydrogen atom. Ground state energy of hydrogen atom is minus 13.6 electron volt. What is potential energy of the electron in this state? I hope you remember the relation, the ratio of energies. Kinetic energy is to potential energy is to total energy of electrons or energy levels of any orbit is going to be equal to 1:2. If you take kinetic energy as 1 unit, 1 joule, then potential energy is going to be -2 unit and total energy will be -1 unit, right? This is the ratio, 1:2 -2 is to -1. Only this ratio is enough to solve these kind of questions. If you know potential energy and kinetic energy, any one of the energy, if you know, you can find out other energy using this ratio, right? In this question, you are given energy, the total energy of hydrogen atom in ground state is -13.6 electron volt, that we know, right? So what is the potential energy? They are talking about potential energy, and look at the relation. Potential energy should be 2 times that of what? Total energy. -1. How can you make it -2? Just multiply with 2. So what is your potential energy in that case? Potential energy is going to be 2 times total energy. It is going to be -27.2 electron volt. Yes. So option B is the correct answer. And here also be careful about the energy levels they are talking about. Sometimes they say second energy level, sometimes they say in the next energy level, sometimes they say excited energy, third excited or second excited, like that. So be very careful when you decide your N value, that matters. Okay, moving on to the next. When an electron moves from 2e energy level to E energy level, right, 2e to E, a photon of wavelength lambda is emitted. Okay. If electron moves from 4/3e to the same E, then wavelength of the emitted, what will be the emitted wavelength is the question in terms of the previous wavelength lambda. All options are given in terms of lambda. So we know when electrons are excited or transmitted from one energy level to the other, right, excitation or de-excitation. So during excitation they absorb energy, during de-excitation they release energy, we know. So here in the first case we have it is changing from 2e to E. So the energy released will be equal to difference in energy of the energy levels. First energy level is 2e and it is coming to E. So 2e minus E is the energy released, delta E. And that delta E is emitted in the form of some radiation, and that radiation has a wavelength lambda. So I can say it is hc by lambda, right? Delta E emitted in the form of radiation of wavelength lambda as per the question. Yes. So we can say 2E minus E is equal to hc by lambda. What is 2E minus E? It is just E. E is equal to hc by lambda. Equation number 1. First equation we got, and we'll take the second case, we'll form an equation in the same way, and we'll take the ratio. That's it. See, look at the second case. In the second case it is transmitted from 4/3e to E, right? 4/3e to E according to the question. And what will be the new wavelength emitted? So hc by some lambda dash I'm going to take. We have to find lambda dash in terms of lambda. Done. So what is, how can you simplify the LHS? 4e minus E, minus 3e, which is going to be E divided by 3, right? E divided by 3 is equal to hc by lambda dash. Equation number 2. Take the ratio. Done. You can take the ratio. See, first equation is E divided by E by 3. That is the LHS of equation 1 and 2. RHS is hc by lambda. Yes, hc by lambda divided by hc by lambda dash. Hc by lambda dash. So we can cancel hc. 1 by lambda by 1 by lambda dash is going to be lambda dash by lambda, correct? Lambda dash by lambda. And what about this? E gets cancelled. 1 by 3 becomes 3. So 3 is equal to lambda dash by lambda. What is your lambda dash now? 3 times the initial wavelength. So the new wavelength emitted will be 3 times the initial wavelength emitted. Okay, that is the final answer. Yes. So when electrons are emitted from when electrons are transmitted from one energy level to the other, they emit energy which always can be equated to hc by lambda or h into nu, right? In terms of frequency, we know, right? So let us try one more question. The ratio of maximum frequency and minimum frequency of light emitted from Balmer series of hydrogen spectrum is. See, this is also one of the like important type of questions. In a given series, we have Lyman series, Balmer series, Passion, Bracket, and Fun series, right? And we learned that in detail, like how this transmission happens. So in each transmission, what is the lowest wavelength and what is the highest wavelength? Most of the time, we will be asked to find ratio, like in this question. And specifically in this case, it is Balmer series. And we know how Balmer series are formed. Balmer series is produced when initial orbit is 2 and final orbit can be 3, 4, 5, etc. Any value higher than 2, right? The second energy level. And we know from Rydberg's formula, 1 by lambda is going to be R into 1 by Ni square minus 1 by Nf square. You're asked to find what is the maximum and minimum wavelength, and we have done this during the revision also. Like, you know, in any given spectral series, spectral lines, the maximum wavelength is similar, like that correspond to minimum frequency transition. Minimum frequency transition is actually minimum energy transition. Yes, minimum energy transition. So it is from the nearest orbit energy level to the second energy level. That is, n is equal to 3 to n is equal to 2. Since it is Balmer series, the nearest possible transition is from 3 to 2. That corresponds to maximum wavelength, right? Maximum wavelength. And what about minimum wavelength? Minimum wavelength is actually maximum frequency. Maximum frequency is when it is coming from infinity to n is equal to 2. So this will give you minimum wavelength. Don't be confused. Minimum wavelength is for maximum frequency, maximum energy, and maximum wavelength is for minimum energy or minimum frequency. Yes. So let us move on to the max. If I go for 1 by lambda max, what is 1 by lambda max? R into, for maximum transition we have 3 to 2, right? Transition 3 to 2. So 1 by Ni. Ni is 2, so 1 by 4, 1 by Ni square. Minus, what is 1 by Nf? That is 3, so it is 9, right? 3 square. Yes, this is for the maximum wavelength. And we can simplify this. R into like 36, and this is going to be 5, right? Yes. So what will be lambda max from this? Lambda max is the reciprocal. This is 1 by lambda max on LHS. Reciprocal is going to be 36 by 5R. This is maximum wavelength, correct? Yes. So now what about minimum wavelength? For minimum wavelength, we know lambda minimum, 1 by lambda minimum is going to be R into 1 by 4 again, because it is Balmer series. 1 by Ni square is always 2 is equal to 4. I mean 2 square is going to be 4 minus 1 by infinity square, which is 0, right? Okay, so we get this is actually R divided by 4, and what is lambda minimum? Take the reciprocal, it is 4 by R, equation number 2. Now if you take the ratio, you will get exact, ratio of maximum to minimum, maximum frequency to minimum frequency. So wait, maximum frequency you're asked to calculate. If it is maximum frequency, not wavelength, we calculated the wavelength. So if you take maximum to minimum ratio of wavelength, it will be the other way of the frequency ratio, right? Minimum to maximum. So if you want to take V nu max by nu minimum, yes. See, this is how. This is what happens when we don't read question properly. Frequency of, maximum frequency and minimum frequency ratio we have to take. So nothing wrong so far. We have to just take the ratio other way around. Yes. So lambda nu max by nu minimum is actually ratio of lambda minimum to lambda maximum. So what is the ratio? Lambda minimum is 4 by R divided by, what is lambda max? 36 by 5R. Okay, so we can cancel R and R here. So 20 by 36. And we have to get the ratio 9 by 5 from this. Okay. Maximum frequency to minimum frequency, lambda minimum to lambda maximum. Yes, so that is the correct option for the question, right? So yes, B, many of you already solved. Yes, okay, thank you. And we have the similar question for bracket series also, and we'll be winding up now after this. I don't have to solve it here. The only difference is when you go for bracket series, what is the difference? For bracket series, we have ni is equal to 4 and nf is equal to what? 5, 6, 7, etc. Correct? That is the ratio. And we can say in that case, what will be the situation? We are asked to find ratio of maximum minimum wavelength only here. So maximum wavelength, lambda max, is for minimum frequency. Minimum frequency is now 5 to 4, right? The transition from 5 to 4. So what is lambda minimum? Lambda minimum is for maximum frequency. Correct? At that time it is from infinity to 4. You can do the same thing which we have done in the previous question. On simplifying, you get 25 by 9. I hope yes, you try. Okay, so this is how we solve the questions from different spectral lines, and by this question I hope we can just wind up today's session. And we have 4 or 5 questions from Nuclei that hopefully we'll do some other time. And thank you for everyone for being with me and for your responses. Hopefully we will meet with another session later. Okay, thank you and good night.